So here we will look at a vertical ellipse, and I'm going to use this one here, number 33. I almost said eclipse, but there is a relationship between eclipse and ellipse, by the way. So I'm going to use this one here. I've already prepped it in Symbol Lab. I hope I did it right. Let's see, minus 200 plus 96. Oh, minus 200 is the only one negative. There we go. There it is. Hit the go button, and Symbol Lab analyzes it. And if we show the steps, then we can see that here. So again, completing the square twice. First, rearranging the terms. So 25x squared minus 200x, and then plus 16y squared plus 96. Factor out a 25 here. That looks pretty nice. There we go. Factor out a 16 here. That looks pretty good here. And by the way, take the plus 495 to the other side and make it negative 495. Eventually, on the other side, by the way, we get a 1. But that's a little bit away here. So here we're going to look at negative 8 divided by 2 is negative 4. Square that, which is 16. A few steps down, you see the 16 right there. Then here we're going to have 6 divided by 2 is 3. Square the 3, so plus 9. And we see the 9 way down here. There it is. There it is finally. And then what they do with the factors in the front, they divide by 25 and they divide by 16. And you get these really strange fractions here. And then because we're completing the square here with the plus 16, that's why we also need to do something to the other side. And here we're adding a 9, so we also need to do something to the other side. You kind of see that here with the 16, and here with the 9 and the factor in the front. And then they do a bunch of algebra. Here's the completing the square, right, from the y right there. That's why they did it this way. And you can also see here's what happened with the x squared, and there it's condensed to this one here. And then at the end, you get the equation of an ellipse. I think the last one is kind of like this one here. So the center is at 4 and negative 3. And then we're going to have 7 over 5 is the major axis, and 7 over 4 is the minor axis, relatively small. So I'm going to try to graph that with Desmos. So 4 and negative 3 is my center. So 4 there, and negative 3. I guess that puts me in the third quadrant, fourth quadrant actually. There we go. And now I think my major axis was, oh, actually it's not my major axis. Now it will become my minor axis. Actually was 7 over 5, which is 1.4. So I hope I'm going to get there. 1.4, there we go. And then the other one was 7 over 4, which is 1.75. So it's going to be here. I don't think I can get to the, there, it's close enough. Ooh, and then it does something with the foci. The foci actually are kind of wrong now. I have to think about that, how I fix that. Give me a moment. I think it's easy. All I have to do is minus c must go away here, and it must be there. Yep, there it is. And at the plus c goes away here, and it goes to the y. So the person who wrote this little thing here for Desmos didn't accommodate for that. But, you know, that's really good what this person did. And that's the vertical ellipse. And again, the reason is that the b over here, the denominator for the y in this case, is actually the larger one. All right, let's look at a few applications. So I'm going to go back here to the book and down here. There's such as medical technology, a lithotripter. There's a device that breaks up kidney stones. Oh, okay. Look at it in just a moment. An arched bridge may have the shape of the top half of an ellipse. In astronomy, we do a lot about ellipses because planet orbits are ellipses, and this particular one is really kind of interesting to me. When I stared at this a year ago, I was thinking, really? These numbers for the major axis and minor axis are so close to each other. There's barely a difference. There's just a difference of 700 miles over a total of 477 1,000 miles. And so I looked it up, and this one here is on Wikipedia, the orbit of the moon, and it used to say right here that the orbit of the moon is quite elliptical. And this particular sentence that you see here, which doesn't say that anymore. It doesn't say quite elliptical. It says nearly circular ellipse, and we can see it in this drawing. So this particular, sentence, I wrote that for Wikipedia, and I also put the diagram in here, and notice that, yeah, it's really a circle. There's the moon, by the way. And the Earth, it's actually not at the center, but that would be one of the foci. And notice that here we get this tiny difference for the axis, the major and the minor axis, 0.16% off, but the what's called the eccentricity of an ellipse produces foci that are 12% off, which is a whopping thing. So this one is actually 12% closer to the other side than it is to this side here, or 6%. And after I did this drawing here, which probably took me half an hour, I clicked on the German website for Wikipedia, and it basically says the same thing as basically the same drawing that I did, just in the opposite colors, right? So I could have just copied that. Oh well. Now I got my own drawing on Wikipedia. By the way, if you look that up, orbit of the moon on Wikipedia, and you go behind the scenes under view history, you will see my name. Okay, another one that goes with it is, let's see, this one here. This is my Desmos. I made this one. And when we look at these orbits of the planets, then we learn in school that these orbits are supposed to be elliptical, and they are, but I'm going to turn a lot of stuff off here. There we go, and I just leave this one. Look at the orbit of Mars. If we don't get a circle out of that, I don't know what. Notice that the equation is actually an ellipse because it has two different denominators. But look at the denominators. 1.524, 1.517. I mean, they're so close to each other, you cannot tell that this is a circle. In fact, if I turn off, I think, the grid and the axis here, and the axis, there we go. And I mean, it's definitely looks like a circle. You would have to measure really, really accurately in order to figure that out. Same thing for the Earth, by the way. This is the Earth's orbit. Okay. It's just amazing. So we learn that here. In fact, it's called Kepler's first law, that the planets orbit on ellipses, but it just so happens in our solar system, the planet orbits are really almost circles. So let me actually go somewhere else, and you can look at the other orbits here as well. And so I looked up this one here, kind of like, why are the orbits of the planets in our solar system nearly circular? And one person argues here, I thought it was in this one here, that circular orbits have the minimum energy for a given angular momentum, and that's a kind of like a physics lesson. And they also put in here that over the development of the solar system, as the planets perturbed, which means gravitationally also disturbed each other's orbits, they actually put themselves into circular orbits. And again, it probably goes back to this particular statement here. Circular orbits have the minimum energy for a given angular momentum. Angular momentum is kind of like how something rotates. And it's kind of like also called the ice skater effect. You know, the ice skater is pulling her arms in, and then she rotates faster. So it has to do with that. All right, I'm going to return to the planet orbits here in a little while, but let's look at something else that I had mentioned here. So here's the medical technology, a lithotripter, and then there's the reflective property, and lab says reflective properties, and those kinds of things. So in a previous lecture for my class, I had prepared that. Unfortunately, I only have access to the PDF instead of my original smartboard. So here you have somebody bathing in some water, and then here you have, this one here would be the sound source, and notice it's at the focal point of this half ellipse here, and then it reflects off the ellipse and it comes back in the focal point of that same ellipse. Imagine that this ellipse continues on like this. So this would be the other focal point, and that's a special property of an ellipse, that when you send it out from one focal point, it will radiate to the other focal point. So that's what's called a lithotripter, and it would then destroy, actually, with sound waves, the kidney stone. Right, here's a whispering gallery. I have this posted in Blackboard, and then here are the circular whispering galleries. So this one here is, oh, where's that? St. Paul's Cathedral, right? So is it, by the way, in London? I think it is, right? And then here are others. There's Grand Central Station in New York City. That's this one here. Then here is, boy, oh, that's the Washington U.S. Capitol. I actually have the Rotunda too. That's on the exam. And then this one here is an arc. And notice, see these people here? They're actually near the focal point. So she whispers in here and he can hear her, or the other way around. He whispers and she can hear him because it reflects from one focal point to the other focal point effectively. Here are actually parabolic whisper dishes. So these are not elliptical, but parabolas do the same thing. So this parabola has just one focal point, and the other parabola you see back there also has a focal point. And so the two can go forth and back. You whisper in one, you hear in the other one. And I got a little upset with one of my sons when we went to a science museum in Columbus, Ohio, and I told him, whisper in here, and your brother is going to listen to it on the other side. Instead of whispering, what did he do? He screamed in the focal point, which means that other kid 50 feet away had a scream in his ear because it went to the focal point, of course. Here, by the way, I don't know where I forgot where that particular bus station is. It's in German here. Maybe it is in German. Yeah, it's in Hanover. So you have these parabolic dishes. So people who are whispering over here, the people over there can hear them. Pretty cool, huh? And here again are orbits. This one here is actually the FET, and I'm going to show that. So this is PHET. It's a very unique one. If you Google PHET, you will come up with all these applets, and one of them is this astronomy applet. And when I hit start here, then the planet is pink planet is gravitationally attracted to that yellow sun there and moves on an ellipse. The sun is in one of the focal points, foci. There's nothing in the other one. That's just the mathematical part over here, but the sun is over here. Notice actually that the sun is also kind of moving on an ellipse. Well, that's a reaction to the gravitation of the pink planet. So the pink planet is attracted to the sun, but the sun is also attracted to the pink planet. As far as the acceleration is, not so much, simply because the sun actually has much more mass than the planet. And again, this one is a fictional one. In reality, the planets orbiting around our sun, actually, their orbits are virtually circular and barely elliptical. And let's see, that was almost what I wanted to say about applications. This one is also, I did this once with FET, I forgot the numbers, where they really disturb each other, and then all of a sudden the orbit is totally different. So here's a lot of that. And this one here, I posted actually as a video, made a link to it. Somebody built an elliptical pool billiard table. And when you put the ball right here in one of the focal points, no matter where you shoot onto the sides, it will always go towards the other focal point, which is where the hole is. And yeah, I advise that you watch this video that somebody made. All right, and that's it.